Hello and welcome back to Calculus2, Chapter 11, Power Series. What we have is the second part, and now what we learned last class as Power Series, I'm just going to call Taylor Series, and if it's centered at whatever A, and if it's centered at 0, we just call that Maclaurin Series is a special case. So what is all of the stuff we learned? It's one and the same thing. Power series are the ones that give you a polynomial on the other end. You get exponents. And we have seen the transformation of a sine function into a polynomial. And I will be writing that again. We will see today e to the x. We will see some other stuff. And then we are going to venture into the calculus of all of these. So before we start with defining Taylor series, in general, power series are given as the summation of some Cn x to the n. N goes, let's say, from 0 to infinity. So we have an independent variable x inside the series, creates the power series, and we also saw last time that the convergence, the divergence of this series depends on the value of x. In some cases, it converges for some x, for other x, the same problem would diverge. So we've seen that with the geometric series and so on. We also looked for radius of convergence, we looked for interval of convergence, so on that particular interval, any x you pick, it would be a convergent series. If you're outside of that interval, it will be divergent. Now, what is a Taylor series? So here, what happened with my colors? Oh my God. More colors. Red. There we go. So, power series as Taylor series. This is redder than usual. Is given by summation, and now you have that coefficient given by the derivatives. The nth derivative computed at a divided by the n factorial times x minus a to the n from 0 to infinity. So your Taylor series now. Where's my purple? Don't call my name in vain. There we go. This is supposed to be pink. Pencil is supposed to be red. This was orange. And it's blue. All right, I think I'm set. So, what do we get on the power series at the other end? If you are using a Taylor series and you use infinitely many terms, then you can say that function f of x is equal to the power series 0 to infinity fn an divided by n factorial x minus a to the n. Equal if you're using infinity of the terms. However, we don't want to use infinitely many terms. What we do is we chop it off after, let's say, 4 terms. If you chop it off from after the 4 terms, then you are using only 4 terms of Taylor series, which means that your function in that case is approximated by the Taylor series, but in this case, all you have is f of a plus f prime of a over 1 factorial, which is 1, times x minus a plus f double prime of a over 2 factorial, x minus a squared plus f triple prime of a divided by 3 factorial of x minus a cubed. This is a 4-term approximation for the Taylor series. And please, here, I'll put it in blood, approximation, there we go, approximation. And this one, if you're using infinity, exact. Now, I did have, last class, I did have, if you watched the last lecture, last stream, I did have that graph where we looked at the sine function and then what happened as I kept adding terms. So if I just had x, that was just a linear line, right? And it was good for a little bit. And then as I kept adding more terms, it started bending more and more around sine to kind of match it. Some of you asked, is this an exact match? Now, here is the answer to that. Yes, it is an exact match if you are using infinitely many terms. Is it exact match if I chop it off? Here is the answer. No, but it's pretty damn good in some area, in some region around the value. So that is the reason why we want to do the centering, right? We want to do the centering at A. Yes?
So for each addition to term, how much more?
Depends on the function, but it is always better. So we don't have the answer of how much, but generally, guys, you are already starting working with the decimal points as soon as you are, the term 3, term 4, you are already really, really precise. So, if you are building anything using your engineering and stuff, you never have to go past 3 or 4 terms to approximate, to change any function into a Taylor series, which is a polynomial, which is awesome, and we'll see why.
Second question, is this how graphing calculators go about?
Yes!
Okay.
Exactly. Pixel by pixel.
I got you.
That's how you would code it. Nice. All right, and then for integration, they just do the 10,000 rectangles. That's, no need for billion, 10,000. Good to go. Maybe even that's too much, but it's okay. So now, Taylor series. We have already seen the transformation of sine. I'm just going to scroll up and say, physics, replace sine x with x for small angles. That's what you heard in physics. And then I said, okay, let's center it at 0, a equals 0. And then I calculate all those derivatives so I can plug them in my 5-term calculation of Taylor series. You see that I have this one as well? Okay, 5-term. Can I add another one? Sure. You can go 7, 10, 13 terms, whatever you want. Simply plugged in everything into where they belong. Plug in the first derivative here. Well, the first derivative is there. Make sure that you are plugging in 0 for x. That's what, all of it's like a double substitution there. And when you calculate everything, we got this. Now, observe that I use the approximation sign because I know that this polynomial is not the same as a sine function. And you saw that on a graph. They diverge from each other eventually, and it becomes really bad after a certain point. So now going back to our Taylor series, what is a Taylor series for sine? So sine x was approximated by x minus x cubed over 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial plus ... No. Well, if I put ... then I have to put equal. So now you look at this thing and you say, well, what's my pattern here? Can I just, mush this into a sum and, right? And the answer is yes. So sine x is equal to summation. You want to start at 0, go to infinity, power series. And now look at your x. X is going to be raised to 2n plus 1. all odd exponents, and the way to portray odd exponents is to use 2n plus 1. So when you plug in 0, 2 times 0 is 0 plus 1 is 1. That's x to the 1, right? And then we are dividing this with the all odd numbers factorials. If you notice, the first one is 0 times 2 times 0 is 0 plus 1 is 1, so 1 factorial under x, right? And then the next one is 3, 5, 7, and so on. So now we are able to write the sine x as the infinite polynomial over here, and if you want to expand it, you get this particular polynomial here. So now, sine function can be written as the sine function, or it can be written as the infinite polynomial. Now, the what? You made yourself a coding project, great. Now, note that this particular sine function was centered at 0 because we only have x. We don't have x minus a, x minus any number, right? It's just x. So that means it was x minus 0, and if it's x minus 0, well, it has a special name. So I'm going to write it in blood over here because it's just a name. It's not a new mathematics. Taylor series centered at 0 is called Maclaurin series. Just a name, right? Maclaurin series. Maclaurin was the first one to do the centering at 0 only, and then Taylor did the center at a, so anywhere. So clearly both names are there, but every Maclaurin series is a Taylor series centered at 0. If you center it away from 0, it's no longer Maclaurin series because Maclaurin did only centering at 0. That's right, that was the first result, and then you make something more general. And then there are power series, more general than Taylor series. And then, guys, you have other series that are not based on polynomials. I did mention that in class. You have Fourier series. Fourier series have trigonometry inside, not polynomials. And then there are other series, right, that you can learn that you can, guys, learn later if you take advanced math courses, graduate level, and all that kind of stuff. So right now, we are only dealing with these. So now the question is, what is the... Let's take a look at the Taylor series for e to the x centered at 2. So this is a Taylor series, and it's going to be centered at 2. My function f of x is e to the x, and then I have to find many derivatives. Well, aren't they all e to the x? Mm-hmm. That's very convenient, right? Yes. Going on forever is just e to the x, e to the x, e to the x, e to the x. Okay. So now, I know that is the derivative calculated at a divided by n factorial x minus a to the n. My a is 2 because it's centered at 2. So now, what is e to the x approximately equal to as I am working on this, right? So, well, first is the 0 term. 0th derivative of a function is just function itself, so it's e squared. Divided by 0 factorial, which is 1, times x minus 2 to the 0, which is also 1, so it's just the first term is just f of a. Plus e squared over 2 factorial x minus 2 to the first power, So guys, this is the term n equal, maybe in different color. Here, blue. This is the term n equals 0. This is the term n equal 1. Now we work on a term n equal to 2. What do I have? I have e squared divided by 3 factorial. Oh no, this was supposed to be 1 factorial. This is supposed to be 2 factorial. There we go, much better. X minus 2 squared. And then we have a cubed over 3 factorial x minus 2 cubed n equals 3 plus n equals to 4 e to the 4 over 4. No, these are all e squares. Oh my god, I'm losing it. I'm losing it, yeah. X minus 2 to the 4th, much better. Plus the dots. Now the dots come in. Oh, because of the dots, great. So e to the x is equal to what? I have e squared divided by n factorial x minus 2 to the n. Oh, I forgot my sum. God damn it. There we go. There we go. Power series for e squared. What is this good for?
Nothing. So, I mean, there's an E.
I said absolutely nothing.
It's good for computing values, and it's really good for calculus, but we'll get there.
Good for carpal tunnel.
Carpal tunnel, yes, killing time. Those are also a good killing paper as well. Yes, I heard that. You're right. Who's over here on a 5th or a 6th notebook by this time of the year, right? This is pretty much everyone, right? Good, yes.
I bought an extra large one for this class.
Just married. That's good. Yeah. Or it was exhaust. It's one of the two. Okay. Now,
Is that the answer?
yeah,
With boxed in red?
that's the answer.
That's the answer?
Why, disappointed?
Yeah.
Oh, so we're not gonna work out any of
I
those?
guess it's just the format.
Oh, because it's going to infinity, you're not really gonna submit, you just.
Ah, there we go. I was trying to figure out where is this thing. All right, great. So now, on page 740, you have the table of Taylor series. And, you need to have this memorized by tomorrow.
Pretty much.
Just kidding. So the Taylor series, all of these, so I just want to show all of them, right? You see all of them. And then I'm going to zoom in.
Yeah.
Okay, so all right. Function 1 over 1 minus x. Right? You can graph this. You can do your everything with that. As a power series has this. 1 plus x squared plus x cubed plus x to the 4th plus. And you can chop it off at some point and have it as approximation. If you go to infinity, you have all possible cases there, and that's it. If you have a plus, you get 1 minus x squared plus x, 1 minus x plus x squared minus x cubed plus x to the 4th, right? So the sign alternates. So How cool is that, right? This one is just 1x, x squared, x cubed, x4. This one is also 1x, x squared, but this one has all pluses, and this one has all minus plus, minus plus, minus plus, which is awesome. Here's your e to the x, which is pretty much the same as this, except it has these factorial denominators, which is pretty much the same as that, right? And it has the factorial denominators. I actually, as a student, was interested in this because I didn't understand any of the stuff, so I tried to memorize them all, me thinking that's going to help. It was actually in differential equations when I figured out. Did I mention you're going to have a chapter on this stuff? Good, because I can show you some things. There are your sine and cosine. Look at this beauty, right? Here's your sine with x minus x cubed over 3 factorial plus x to the 5 factorial. We have that written down, right? Nice. Ooh. Holy nightmare. Guys, I forgot the alternating term. Terrible.
Plus 5.
You mean minus 5?
For you, but plus 5 for us.
Why is that plus 5 for us? For you, I mean. That makes no sense.
Makes sense to me.
Let's vote.
I can't get my pen to work now.
Oh my
To add
goodness.
minus 1 to the end. Help me. Come on. It's falling apart. Is the touch screen working? Yes. Oh, two poor souls are watching this disaster of a class. Nothing is working for me now.
Now, if that was an apple, it'd still be going strong.
I said do not call for me to use Apple. I'll be nasty, so now I have to be. Because I'm not using Apple, I'm not autistic. Well, I asked for not to mention that for all right. Pen won't work.
He's had a question for the last 5 minutes.
Yes. I can't get this. So I need to add this, guys. Minus 1 to go back to the sine example. I just add this in. Minus 1 to the n. What is your question?
You get the chisel on the board and then it's to the k, but for ours we just have b squared.
Because we were centered, right? We were centered at, because when you are centering it at 0, e to the 0 is 1 every time. So you won't show it, right? You won't show it.
Okay.
Now, these ones all have x minus 2 because it was centered at 2, and then e survives because it's e squared every time. It's not, right? Because it's the derivative calculated at a, and your a is 2. So these are all the basic ones that are centered at 0, but mine was centered at 2. So yeah, there we go. Minus 1 to the n. I just added minus 1 to the n. Minus 1 to the n to catch the alternating term. Of course. I know, leave me alone. I'm having a crazy day which started at 7 with like everything that can go wrong went wrong, and now it's just bombarding me with Apple crap.
It's got a whole spirit. Now you know how I feel when it comes to this.
We are getting slowly to the inverse tangent, so relax. So sine and cosine, guys. Now, I have to ask, this is the time where I ask the question, what can you tell me observing the power series of sine and cosine? Is there anything that you learned about sine and cosine in your pre-calculus course and you might have asked why, and your professor said, you'll know eventually?
That they're shifted.
Nope. So something that you learned in the pre-calculus. So look at their power expansions, right? And it answers the question that you might have had, I think you thought about these things, about a property of sine and cosine functions. What was someone said something over here? Even and odd functions. Sine was defined as what?
No.
Odd function, right? Why? Your professor said, don't worry about it. It just is. Because the property of f of minus x is the same as minus f of x. It holds that property. Why? You'll know later. That's the best answer they can give you, we can give you at that time, because I can't really, I mean, if the student is persistent, I'm going to write this because it's me, right? But look at your powers. Odd, 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 and look at the 2k plus 1, that's odd, which is why sine is odd function. And how about your cosine? 1, that's a 0. Even, 2k, that's even, right? So all of the powers in cosine are even powers, and that's why cosine is even function. Just like your x squared is even function. It's symmetric on the y-axis. It's awesome. So there is one of your questions that you wondered about. Yes?
Out of curiosity, since sine over cosine is tangent, could you technically put one summation over the other summation?
Yes, but dividing them is you're dividing infinite polynomial by infinite polynomial is not going to be pretty.
No, okay, I got you.
So you actually go and you work out your calculation for expansion of tangent, and you take a look at the tangent series, which are pretty much useless, but it can be done.
Oh,
It's on the lab.
Exactly.
Yes, it is.
I know. Someone put them there.
I know.
ln of 1 plus x gives you the nice x over 1, x squared over 2, x cubed over 3, x4 over 4 with alternation in between. Then 1 minus x gives you all pluses. The same like you had up there. Inverse tangent is with us tonight in the house. And we have the sine hyperbolic and cosine hyperbolic. Guys, if you are taking differential equations in chapter 3, you will need to know the Taylor expansions for sine, cosine, sine hyperbolic, cosine hyperbolic, and e. Right? Those are the 5 that you absolutely must know if you are taking difficus, because in difficus, as I will show you later, you have ability. The way you solve a problem is you actually get this side as the answer, and then you come up with this, which you recognize as that. So your calculation is going to give you that. You will have to squish it into this. Now, in differential equations, what happens is that you actually get this and this together in one, and then you separate the terms for this one in one and for that one in the other, put a big fat plus in between them, and then the first one you compress into this, the second one you compress into that with a plus in between, and then you put this one plus that one as the answer.
Oh.
Welcome to differential equations, right? So that's chapter 3. And if you guys don't, if you guys don't do that, then it's an issue. Yes?
You were saying the expansion of the inverse tangent as putting it as sine over cosine?
No,
No.
not inverse tangent. Tangent. Tangent is sine divided by cosine. But in that case, you are dividing infinite polynomial by infinite polynomial, which is not something that...
So that right there is the expansion of inverse
Inverse tangent, yes.
So-
Inverse tangent.
If
Okay.
you know, if you're centering it and you say create sine like that, and you do so many terms for a certain given area, that's exactly sine.
Yes!
So if you integrate that, then technically that will give you
We are getting there.
cosine.
Yes. We're getting there. So, the idea of these power series is to take your function, which is your transcendental function, like logs and e's and sines and cosines and hyperbolics, and turn them into a polynomial.
Which you can easily
which you can easily differentiate and integrate. Now, many of you will fight me on this because you say, hold on, e's are much easier to integrate and differentiate than polynomials because e just stays e, right? But you very rarely have e, right? You very rarely have e. You have e times some other stuff, right? And if you turn all of that stuff in polynomial, well, then you got to do some foiling, and then you integrate and differentiate. You don't have to worry about product rule. You don't have to worry about biparts. You don't have to worry about any of the exquisite stuff we did in this class. You take the entire course, wrap it up, put it in the garbage, and just know one page, right, of power series. Because you are replacing your entire knowledge of all functions possible with exactly, right? So, yes.
Why don't you just teach us this in the beginning?
Would you go about,
We had to build up to it.
how would you go about integrating or taking derivative of a factorial?
There are, look it up. There are ways.
Are we going to go over this?
No.
No, okay.
Now, we are now need to talk about the remainder from this calculation, because if you are approximating, you are making an error. And they're not exactly the same, right? So what do I have? I have the ability, I have the error, most of the error concentrated in the first term that I am throwing away. I hope that makes sense. So, what I showed last class is that as I add more and more terms to that sine series, power series, the graph bends more and more and mimics sine more and more on both sides, right? And eventually, the lines diverge from each other, right? Now, the remainder works this way. Call it R of x or whatever. Did they call it R of x in the book? I think they're calling R of x. Yeah, Rn of x. Not sure on which page, but guys, this is just the next term. So if you are keeping n terms in your Taylor series for your calculation, most of your error will be focused in the first term that you are throwing away, which will be called the n plus first term. So the remainder is approximately equal to the n plus 1 derivative computed at a divided by n plus 1 factorial x minus a to the n plus 1. So this is just the next term or the first term you're throwing away. So most of the error is going to be focused in that particular term. And if you need to calculate what the error would be, you just use this formula. So just go to the next derivative and you plug all of the variables in, and you will be able to calculate your error. It should be 0.000 something, right? If you are using 4 or 5 terms, it should always have a couple of zeros before you hit significant digits, which would represent, because Taylor series converge very fast, guys, and the error that you're making with the 4 or 5 term calculations are insignificant in every aspect of existence.
Everything before this would be 100% correct.
No, because you're chopping it off, right?
Well, that's what I mean.
Oh, you mean after this?
Would be like, yeah.
Because there is plus infinite amount of terms here. And then if you add this to the Taylor series, because remember,
No, so what I'm trying to say is when we had the say we had 3 terms like we did in class, where we got so much of sine and then it kind of diverged away.
No,
How
it
much
is
is that?
not 100% on top of the line unless you use all infinity of the terms. They look on a graph, they are, because they are matching at the 4th or the 5th or the 6th decimal, right? So the graphing utility is not going to graph it and show you difference because you are 0.00003 off, right?
So it's negligible.
So it's completely negligible. You use 4 or 5 term expansion, the numbers you are getting are not exact, but they have the error on the 5th or the 6th decimal, right?
Oh, okay.
So, and if you want the exact number, you have to use all infinity, but you're not going to sit there and calculate the infinite amount of terms. So, if you are using 4-term approximation, then your 5th term is this term, and this term is going to carry most of your error. Because the next term is going to, again, go decimals away. So that's the remainder, and this stuff is, so I'll say most of the error is here, right? That's it. Most of the error is here. In that one term, which is the first term you're throwing away, that's the one that has most of the error. Like, think about that for rounding, and you have numbers, right? And you chop them off, right? Don't you agree that each digit is 10 times, right, the next digit? So most of the error, right, 10 times at least, is there. Good, because the next one is 10 times smaller, the following one is 100 times smaller, the following one is 1,000 times smaller, as you keep, yes, pushing the decimal back. So most of the error will be concentrated in the term that you throw away. So that's the remainder and error calculations, and it's as simple as you just calculate the next term, plug the numbers in, and you're done. Calc. So, I know.
Peter saw that. Is that a joke? I said, no, it's not.
Yes, he belongs to the movement that that wants to bring back the letter, right? Because cat should be spelled with K, not with C. It's not cat, it's cat, right? It's not fair.
You got a point.
I know, right?
Yeah.
And then you use K in all of the words that are silent, like night and knife, right? You don't say knight, you say knife. You can't even hear it, but you spell it with K. It makes no sense. As a foreigner, I notice these things. So bring back K. Anyway, so calculus, 2 Ks, no Cs. What do we have, guys? So remember that one function that we said we're not going to integrate because it can't be integrated? We talked about it, I believe, when we talked about by parts. I said the integral of e to the x dx, then I said the integral of e to the x squared dx, then I said the integral of x e to the x squared dx, and then I said integral of x e to the x dx. So you are looking at the 4 different integrals here, 4 different integrals, and which one you can't do? Which one? Number 1, number 2, number 3, or number 4?
4.
Number 2. What's number 1?
E to the x.
Just basic, right?
Plus 6.
What's number 3?
1/2 e to the x.
Well, not the answer. What method? I mean,
Substitution.
U sub, basic U sub. How about number 4? Yeah, the final is coming up. That might be on it. It's by parts, right? You go U is x, and then derivative will kill it, and right? So that's by parts. So first one is basic integral from Calc 1. Third one is the U sub, again Calc 1. And then the last one is the by parts. The only one that you can't do whatsoever is the second one. right? And you see what's missing. You are missing an x in front to make it into a u sub. There is nothing that you can do except for, let's see, the power series. Hello, power series. Because what is my expansion for, we don't need to be dramatic. What is my expansion for e to the x? We just said what it is, right? It was 1 plus x squared over 2 plus x cubed over 3 factorial plus x to the 4 over 4 factorial plus I got bored, right?
Could be 2 factorial.
Now, what do I need to swap?
2 factorial.
2 factorial is 2, sure. Right? 2 factorial is 1 times 2, which is 2. 3 factorial is 6 and 4.
Yeah.
You want the consistency.
Yes.
Do you see the little x squared over here? Now I'm dramatic. Now that is going to run through this equation and replace all x's with x squared. Ooh. And then you integrate the polynomial.
So it's going to be x squared to the second?
Yep, it makes it a joke. So now I have 1 plus x squared plus x squared squared over 2 factorial plus cubed plus the 4 and plus dot dot dot, and each one of these has the little x squared inside. If it was e to the flower, each one of these red x squares would be a flower. Whatever the exponent is turns into these guys. So now what do I have? I have that my e to the x squared is 1 plus x squared plus x to the 4 over 2 plus x to the 6 over 6 plus x to the 8 over 24 plus dot dot dot. You only use 4 terms.
Well, in this case, yeah.
That's when
I'm
you
saying
stop.
like later.
No, you don't do later.
Never?
No, why would you?
Oh.
You're okay with 4 to 5 terms. Don't make this difficult for no reason. I didn't lose it. I calculated them now.
Yeah.
You see that in the line where I had the red x squares, the factorials were still there, and then I just calculated them in next step. 2 factorial is 2. 3 factorial is 6 because it's 1 times 2 times 3. That's 6. Right? So I just computed. 4 factorial is 24 because 6 times 4, next number. So I just computed the factorials. Guys, integral of e to the x squared dx is approximately the same as the integral of 1 plus x squared plus x to the 4 over 2 plus x to the 6 over 6 plus board dx.
That's the answer?
No, now you have to integrate.
Oh, son of a comedy black.
No, but that's a joke of an integral.
So integral of 1 is x
X.
plus x cubed over 3 plus x to the 5 over 10 plus x to the 7 over 42 plus dot 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 plus c or minus 1, whatever you want. Okay? So, for you, minus 4. So now,
Something like that on the exam?
yes,
Just
this,
like that?
yeah,
Cool. That's easy.
of course. This is Power Series. It's really cool. Like, if you don't think this is cool, you should quit your major. Because Calc2 is the part of your major. This is extremely cool. And we, guys, but what you need to appreciate is that we took something that we can't integrate at all, and we just made a joke polynomial out of it.
Mm-hmm.
Yes?
I have a question. How did you get the first step?
Which first step? This? This? I memorize it. If you don't know it, you do this.
You go to the page.
because it's a Taylor series. Yeah.
Yeah,
So the Taylor series are known. And if you don't know them, you calculate them on the side. So the ones that, because I said it already, the 5 series that you need to know when you're going to differential equations: sine, cosine, e, sine hyperbolic, cosine hyperbolic. Right? Those are the 5. You might want to memorize those 5 for next week. Right? Might. Because they're very, guys, they are the same.
This isn't a poker game. Just tell us if we have to memorize them or not.
He's very strict.
The difference between sine and sine hyperbolic is sine hyperbolic doesn't have the alternating term. The difference between cosine and cosine hyperbolic is cosine hyperbolic doesn't have the alternating term. They look the same. And then, so the power series are sine alternates each sign, and sine hyperbolic does not, all pluses. So if you know sine and cosine, you immediately know hyperbolics, because they don't change signs. And the only one that you are memorizing in addition to that is e to the x. So you can do these calculations. Let me give you another one. Do we all remember the evil problem?
Oh, that sine, cosine, the one that
Yeah, it used to be a whole page of calculations. You love this problem. It was e to the x, sine x, dx, and what you had to do here is a page of calculations, and then you eventually do the integration by parts twice, and then you take that term, bring it to the other side, then you divide both sides by 2, right? How long does it take us to do the power series? 2 lines. 2 lines. That's all it takes to do the power series, because you already know that your e to, well, you will learn, that your e to the x is 1 plus x squared over 2. Chop off the rest, throw in the garbage. Times, you know that your sine is x minus x cubed over 3 factorial, which is 6, plus x to the 5 over 120 dx. Foil. And then integrate. You kidding me? Right? There's no more calculations, no more integration by parts, nothing. So,
Give us something like that on the exam.
of course you're getting it. You have to
Just
get it.
that problem.
Multiply,
That's it. We're good.
then integrate. I told you last class, power series, because it's x to the power of n, but I understand it as power series, right? Because it just takes all of the stuff that you guys learned earlier and grinds it into nothing. It turns these problems into polynomials. Polynomials you can FOIL, you can factor, you can distribute, you can do whatever you want, and then you just integrate the polynomial, right? Are you going to change basic problem e to the x into this? No. Integral of e to the x is e to the x. Integral to e to the 3x is e to the 3x over 3. You don't change those because those are cheap. But when you get to e to the x squared, when you get to even the, okay, how hard is to integrate the power series problem, not the power series, the by parts problem over here? U is x, dv is e to the x, plug in, right, and go. Why? This one in 3 terms is this times this times this times x. That's x squared, x cubed over 2. Boom, integrate. Good enough for engineering.
Let's just say we have a problem like that on the exam and it says integrate by parts. Can we just use the power series?
It said integrate by parts.
But
So you answered it for yourself. It said integrate by parts.
it's easier.
I agree.
Out of curiosity,
Yes, Apple boy.
what's
Man knows quality.
So, like, if you were.
Hold on, he already started. I was just
Boston.
Yeah.
What's it called? There was an interval that came up somewhere, and it was secant cube, which doesn't simplify nicely. Could you technically?
Well, if you know the power series for secant cube, yes, which is 1 over cosine, which is not nice, and yeah. So yeah,
it would be much easier.
everything can be, yeah, everything has its ins and outs. So you have to weigh what is more economical.
So would that be easier to do that specifically?
I don't know, but it's integration by parts. So yeah. What do you have?
Well, I was just like talking about what she was saying, like on the test, like if you were to say like integrate the partial, what if you were to do it like this, and you still get the right answer, like, are you?
Well, you're not going to get the right answer doing this because these are approximations. You have to be very careful about it. These are not right answers. These are the best answer under the circumstance that you want to be lazy and you won't actually want to do the full work, or in case of e to the x square, you don't have other option, right? Because these things will provide you the best answer possible under the circumstances, but they do not give you exact answers. Now, there are other issues that you guys might not consider. You see, if you have a definite integral from, let's say, 0 to 3, right? 0 to 3 of, let's say, e to x squared e to the x dx. And you absolutely, hence lazy, don't want to do your integration by parts twice and then mess with the limits. You're going to say, oh, I know the power series for e, and this is just multiplying x squared, is going to be a joke. So I'm just going to replace my power series for e and do the x squared times, don't write this, 1 plus x squared over 2 plus x cubed over 6 dx, and now distribute my x squared. That makes a square, a cube, a fourth, and a 5 over here. Wrong. Because you integrate this, and you get your x cubed over 3 and plus x to the 4 over 4, and you go on, and you plug in 0 to 3. Wrong. Because you centered your integral, you centered your power series at 0. Where's the center between 0 and 3? Only 1.5. You see that? So this is not mindless plug and chug. You have to be very careful where are you using these things. If my integral was 0 to 0.1, hey, great, right? This is going to work. But 0 to 3 or 0 to 10? No. And also, you actually have to graph and see, okay, 0 to 10, I'm centering at 5 because that's the middle. Now, how many terms do I actually have to put so that it bends these functions enough on 0 to 5? That's now trial and error. So there is no free lunch. Power series are great in approximation, but they can be very nasty if you are dealing with the definite integrals, because you have to be careful and center them at the appropriate place.
So out of 10 points, you get 8. That's good.
In engineering, what you get is a battery that explodes or the bridge that falls down and kills people. So, and you get to make that mistake only once and you never work again.
That is true.
So there's that, right? Just like a nurse who says, I hate math. Oh, great. The first time you calculate the dose and you kill someone,
Oh my God.
guess who's not a nurse anymore? After going to school for 5-6 years saying, I hate math, I hate fractions, I hate this. No, because, right? So as engineer, right, you have to understand that thousands of people are going to go off the bridge that you make. You get to center your power series, right, where it needs to be centered. It's very simple, right? Otherwise, that bridge is not going to stand for too long, right? Now, cool thing. What's the derivative of sine? X. Why? Right? Because Calc 1 told you so.
You memorize.
right? And then you memorized it, right? And then we did that f of x plus h with the h goes to 0 limit, right? We did all of that stuff. Cool, right? Yeah. How about some power series? We can handle that. So what's the derivative of x minus x cubed over 3 factorial plus x to the 5? Do you see when you take the derivative, it's going to land on all evens? Minus x to the 7 over 7 factorial plus x to the 9 over 9. I promise I'm going to start. Plus, minus actually. So what are the derivatives here? Derivative of x is 1 minus the derivative of x cubed is 3x squared, and then you have 3 times 2 factorial. The 3's cancel. Plus 5x to the 4 over peel off 5. Leave the 4 factorial there. Boom. Cancel. Minus 7x to the 6 over 7 times 6 factorial. Cancel. Plus 9x to the 8 over 9 times 8 factorial. Cancel. Minus 3 dots.
Wait a sec, so all you gotta do is memorize just sine, and then you can derive cosine. You could probably...
And then your hyperbolics works the same.
How does the reciprocal identity work for all those?
No, it does. No. They're minus and plus. No. Absolutely not. So do we see now why? Right. So now, if you take a look at this, what is this? This is a summation. I'm not gonna forget you now. N plus 1, x to the 2n divided by 2n factorial from 0 to infinity, which is your dear beloved cosine x. So derivative of sine is cosine. So next time if you're tutoring someone in Calc 1 and they say y, it's clear as day. There is a course missing in between, but obviously. Now, my favorite, your favorite, everyone's favorite, the derivative of a to the x. That was a good one. So, 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus ... equal to the derivative of 1 is 0 plus the derivative of x is 1 plus the derivative of this is 2 times x divided by 2 times 1, cancel, plus 3x squared over 3 times 2 factorial, cancel. Look at that. You got it. It's the same, right? 1 plus x squared over 2 factorial plus. So derivative of e to the x is e to the x. Because you got the same power series when you differentiate. This is insanely cool. When I saw this as a student, it looked so fascinating. I didn't understand any of it, but it looked so fascinating because, you know, all of a sudden, all this mathematics, they should be clicking in. It doesn't, but it seemed like, you know, my professor was very, you know, excited. So I picked up on that excitement, and I was excited even though I had no clue what was going on.
That's how we feel right now.
Remember,
Eventually in time.
remember how we did the equations for E for trig and hyperbolic trig?
Uh-huh.
Is that where this comes from?
No.
No, but can you, from those equations, get the same?
That's something completely different. I'll show you later. It's completely different.
Okay.
So now you guys, you have seen power series. Power series have this x, and their convergence depends on the value of that x, which is why we have to look for radius and interval of convergence. We use ratio test for that. The power series that we are looking into, which produce these polynomials, are called Taylor series. If you center them at 0, well, we just have a special name called Maclaurin series. All of these were Maclaurin series because you don't see x minus a anywhere. It's just x. If you just see x, right, then it's Maclaurin series because it's x minus 0, which is x. If x minus 3, x minus pi, x plus pi, then it's centered at that value of 3 or pi or whatever, and then it's a Taylor series. But everything is a Taylor series, even Maclaurin series are Taylor series. So we know the formula to convert any function into a Taylor series, which gives us a polynomial on the other end. You just need to find a whole bunch of derivatives and compute as many terms as you need, as you're requested, or right, whatever is assigned. And then once you have the power series, well, you actually have a polynomial, in which case taking limits, taking derivatives, or integrating them is a joke. It is good to use this in the tough problems where you really don't have the closed form for the integral, like e to the x squared was a great example because you can't integrate that with any of the techniques that you currently know. Are there ways to do this? Yeah, there is a little hack way that you can do it in Calc 3, but we'll see who gets there. And remainder, right, for the Taylor series is just the first term. So most of your error is going to be concentrated in the first term you throw away. So if you are doing a 5-term expansion, then the 6th term is the one that has most of the
Are we going to have
error.
remainder on the exam?
Could. Why not?
Why do that?
Because it's easier than a lot of other stuff.
No. Why
Because if you are looking
why
for a
does-
Taylor series of 5 terms, you are calculating 5 terms. If I'm asking you for the error, you're calculating 1. That's 5 times faster. There's the argument there.
I don't like this.
You should be more clear cut.
Yeah.
I will
Like
see
the
Nikki
curve,
next week. So
Horrible.
Are we done?
are we done? Well, I guess you want to be done.
We should get a study packet.
Study packet.
Review.
Yeah, it's there on my MATLAB. I'll show you now.
Oh.
Bye.